Hello. Hello and welcome to this video on the standard library of Rust. We will go through hashtag documentation, that is this one. Now there are other ones which we have covered, that is vector and hash map we have covered. Linked list also we have covered. So we will not cover vecdeck, B-tree map, B-tree set. I have changed the plans and I will cover binary heap as well. Now something is missed by me, that is two sections of collections module documentation. So first one is this, okay? So and then this section. So I'll just read this quickly so that we don't miss it. Rust standard collection library provides efficient implementations of the most common general purpose programming data structures. By using the standard implementation, it should be possible for two libraries to communicate without significant data conversion. To get this out of the way, you should probably just use vec or hashmap. These two collections cover most use cases for generic data storage and processing. They are exceptionally good at doing what they do. All the other collections in the standard library have specific use cases where they are the optimal choice, but these cases are borderline niche in comparison. Even when vec and hashmap are technically suboptimal, they are probably a good enough choice to get started. Now this describes further use of vec when you want to collect items to be processed or sent elsewhere later and don't care about any properties of the actual values being stored. You want a sequence of elements in a particular order and will only be appending to or near the end. You want a stack, you want a resizable array, you want a heap allocated array. Use a vec deck when you want a vec that supports efficient insertion at both ends of the sequence. You want a queue, you want a double-ended queue. Use a linked list when you want a vec or vec deck of unknown size and can't tolerate amortization. You want to efficiently split and append lists. You are absolutely certain that you really truly want a doubly linked list. Use a hash map. You want to associate arbitrary keys with an arbitrary value. You want a cache. You want a map with no extra functionality. Use a B-tree map when you want a map sorted by its key. You want to be able to get a range of entries on demand. You are interested in what the smallest or largest key value pair is. You want to find the largest or smallest key that is smaller or larger than something. Use the set variant of any of these maps when you just want to remember which keys you have seen. There is no meaningful value to associate with your keys, you just want a set. Use a binary heap when you want to store a bunch of elements but only ever want to process the biggest or most important one at any given time. You want a priority queue. So performance descriptions we are given here. So I would suggest that you take a look at it at your leisure. So you can pause the video here and read it, or later on also you can go to the URL and read this. Okay, and we will not go further, although it will be beneficial if you go and read all this, but we are not going to do that. What we are going to do is we are going to the hash set documentation. Okay, or I think, should I go and describe this? Okay, we will skip the hash set in this video. We'll just go through the rest of rest of the document in std collections. Choosing the right collection for a job requires an understanding of what each collection is good at. Here we briefly summarize the performance of different collections for certain important operations. For further details, see each type's documentation and note that the names of actual methods may differ from the tables below on certain collections. For the documentation, we will adhere to the following convention for operation notation. The collection size is denoted by n. If a second collection is involved, its size is denoted by m. Item indices are denoted by I. Operation which have an amortized cost are suffixed with star. Operation with an expected cost are suffixed with tilde. Calling operations that add a collection will occasionally require a collection to be decided, an extra operation that takes own time. Amortized costs are calculated to account for the time cost of such resize operation over a sufficiently large series of operations. An individual operation may be slower or faster due to the sporadic nature of collection resizing. However, the average cost per operation will approach the amortized cost. Rust collections never automatically shrink, so removal operations aren't amortized. HashMap uses expected costs. It is theoretically possible, though very unlikely, for HashMap to experience significantly worse performance than the expected cost. This is due to the probabilistic nature of hashing, that is, it is possible to generate a duplicate hash given some input key that will require extra computation to correct. So please go through this table. I'm not going through this because most of it you will encounter when you read the documentation of each data structure. Now we have correct and efficient uses of collections. Of course, knowing which collection is right one for the job doesn't instantly permit you to use it correctly. Here are some quick tips for efficient and correct uses of the standard collections in general. If you are interested in how to use a specific collection in particular, consult its documentation for detailed discussion and code examples. Many collections provide several constructors and methods that refer to capacity. These collections are generally built on top of an array. Optimally, this array would be exactly the right size to fit only the elements stored in the collection, but for the collection to do this would be very efficient. If the backing array was exactly the right size at all times, then every time an element is inserted, the collection would have to grow the array to fit it. Due to the way memory is allocated and managed on most computers, this would almost surely require allocating an entirely new array and copying every single element from the old one to the new one. Hopefully you can see that this wouldn't be very efficient to do on every operation. Most collections therefore use an amortized allocation strategy. They generally let themselves have a fair amount of unoccupied space so that they only have to grow on occasion. When they do grow, they allocate a substantially larger array to move the elements into it so that it will take a while for another grow to be required. While this strategy is great in general, it would be even better if the collection never had to resize its backing array. Unfortunately, the collection itself doesn't have enough information to do this itself. Therefore, it is up to us programmers to give it hints. Any with capacity constructor will instruct the collection to allocate enough space for the specified number of elements. Ideally, this will be for exactly that many elements, but some implementation details may prevent this. See collection specific documentation for details. In general, use with capacity, and when you know exactly how many elements will be inserted, or at least have a reasonable upper bound on that number. When anticipating a large influx of elements, the reserved family of methods can be used to hint to the collection how much room it should make for the coming items. As with capacity, the precise behavior of these methods will be specific to the collection of interest. For optimal performance, collections will generally avoid shrinking themselves. If you believe that a collection will not soon contain any more elements, or you just really need the memory, the shrink to fit methods prompt the collection to shrink the backing array to minimum kept size capable of holding its elements. Finally, if ever you are interested in what the actual capacity of the collection is, most collections provide a capacity method to query this information on demand. This can be useful for debugging purposes or for use with the reserve methods. Then we have iterators. Iterators are a powerful and robust mechanism used throughout Rust's standard libraries. Iterators provide a sequence of values in generic, safe, efficient, and convenient way. The contents of an iterator are usually lazily evaluated so that only the values that are actually needed are ever actually produced, and no allocation need be done to temporarily store them. Iterators are primarily consumed using a for loop, although many functions also take iterators where a collection or sequence of values is desired. All of the standard collections provide several iterators for performing bulk manipulation of their contents. The three primary iterators almost every collection should provide are iter, iter_mut, and into_iter. Some of these are not provided on collections, which where it would be unsound or unreasonable to provide them. Iter provides an iterator of immutable references to all contents of a collection in the most natural order. For sequence collections like vec, this means the items will be yielded in increasing order of index starting at 0. For ordered collections like B-tree map, this means that the item will be yielded in sorted order. For unordered collections like hash map, the items will be yielded in whatever order the internal representation made most convenient. This is great for reading through all the elements of the collection. So you have some code for iter and itermut, provides an iterator of mutable references in the same order as iter. This is great for mutating all the contents of the collection. Into iter, transform all actual content collection into an iterator over its content by value. This is great when the collection itself is no longer needed and the values are needed elsewhere. Using extend into iter is the main way that contents of one collections are moved into another. Extend automatically calls into iter and takes any key into iterator. Calling collect on an iterator itself is also a great way to convert one collection into another. Both of these methods should internally use the capacity management discussed in the previous section to do this as effectively as possible. So here you can see that vector you call into iter and then you collect, you get a vec_dec. Okay, you can specify and you will get it. Iterators also provide a series of adapter methods for performing common threads to sequence. Among the adapter are functional favorites like map, fold, skip, take. Of particular interest to collections is the rev adapter, which reverses any iterator that supports this operation. Most collections provide reversible iterators as a way to iterate over them in reverse order. So here you can see vectors. On a vector, you convert it into an iterator, and then you call rev on that iterator to reverse the vector. Several other collection methods also return iterators to yield a sequence of results, but avoid allocating an entire collection to store the result in. This provides maximum flexibility as collect or extend can be called to pipe the sequence into any collection if desired. Otherwise, the sequence can be looped over with a for loop. The iterator can also be discarded after partial use, preventing the computation of the unused items. Then we have entries. The entry API is intended to provide an efficient mechanism for manipulating the contents of a map conditionally on the presence of a key or not. The primary motivating use case for this is to provide efficient accumulator maps. For instance, if one wishes to maintain a count of number of times each key has been seen, they will have to perform some conditional logic on whether this is the first time the key has been seen or not. Normally, this would require a find followed by an insert, effectively duplicating the search effort on each insertion. When a user calls map.entry with a key, the map will search for the key and then yield a variant of the entry enum. If a vacant entry is yielded, then the key was not found. In this case, only valid operation is to insert a value into the entry. When this is done, the vacant entry is consumed and converted into a mutable reference to the value that was inserted. This allows for further manipulation of the value beyond the lifetime of the search itself. This is useful if complex logic needs to be performed on the value regardless of whether the value was just inserted. If an occupied entry is yielded, then the key was found. In this case, the user has several options. They can get, insert, or remove the value of the occupied entry. Additionally, they can convert the occupied entry into a mutable reference to its value, providing symmetry to the vacant insert case. So here we have an example. So we'll see plenty of examples. Okay, don't worry about examples. We'll have plenty of examples. So what I think is that B-tree map is basically an ordered map. Okay, in terms of C++, if you think B-tree set would be an ordered set. So I think that it would be useful for us to go through these. So we will, in the next video, we will cover hashed set, and then we will go for binary heap. Then we will follow with vec_dec, B-tree map, and B-tree set, and then we will move on to iterators. So I don't think we have time left to cover hash set. So we will see this in the next video, that is after 4 days. So I hope that you have learned something about Rust standard library collections and found something useful for yourself. So with this, I will end this video here, and I'll see you in the next one after 4 days. Till then, stay curious, keep learning, and most importantly, enjoy.